Thanks a lot, Priyanka, for the very kind introduction, and thanks a lot to the organizers for inviting me here. I've just arrived 2 months ago, so I'm very excited to reconnect with my old friends and build many new friendships and collaborations. So today I'm going to be talking about a project which I'm really very passionate about. And I've spent the last 6-7 years working on this all-sky mission, end-to-end, right from operating the missions to processing the software to calibration, and then actually utilizing the science to write papers. This is called Counting the Invisible, as you can see, because I work in the X-ray wavelength primarily. So I just wanted to build a view graph to see how far we have come with respect to X-rays. So this is a relatively new field from the 1960s. So this is a map from the 60s, from the first Uhuru catalog, where we have 300 or so bright sources projected against the sky. And now we can boast of many millions of sources. So let's move ahead. So the universe in X-rays, I mean, we need to go to space for that because it is absorbed by the Earth's atmosphere. So we're talking about a very narrow range of temperatures around 10 power 7 to a few times 10 power 8 kelvins, and energies around, let's say, 0.1 to maximum 100 kilo electron volts. So what can we boost of understanding in X-rays? It's mainly hot and energetic universe. But the structures we can, or the objects we can probe mainly are shock heated gas in supernovae, accretion powered in X-ray binaries. This actually powers one of the most brightest sources in the X-ray sky, and X-rays from free electrons. So just acceleration of a charged particle or synchrotron due to moving in the magnetic field, or just Bremsstrahlung due to accelerated by another photon. So I already said that what we are talking about is typically energies of 0.1 to 150, but this is really stretching the limits. What we are most sensitive in the current generation telescopes realistically is, say, 0.2 to 50 kiloelectron volts. And with respect to imaging, because you see these beautiful images here, we have mostly remained confined at energies less than 10 kiloelectron volts, with other than a few exceptions, of course. I will just briefly touch about why. So let's look at this first X-ray source catalog or image. So this is a catalog of 339 X-ray sources. You see the galactic plane here. So the circle sizes are just scaled with intensity. So this is the galactic plane. And as I said, most of these objects that you see here clustered here are X-ray binaries powered by accretion, either by an early type star or a late type stars. And then at the high galactic latitudes and more uniformly, you see mostly active galactic nuclei. So the way to build this map was using the concept of proportional counters. So large area detectors where you have a gas-filled proportional counter where charges fall on the detector, and usually by photoelectric absorption, you have that charge absorbed, which produces a cascade of electrons. And the number, roughly the number of this signal or this electrons produced can be deduced back to the energy of the incoming photon. So here you have very limited spatial resolution because you do not know really within that field of view where the X-rays came from. So how to, sorry for the slide, this did not look like that in my laptop, but I can just briefly go through it. So how to increase the signal to noise spatially in that way. So roughly we are in the Poisson statistic regime where we count the photons. So we can either, of course, keep on increasing the signal or reduce the background. So what would help in this regard is focusing, trying to focus the X-rays in a smaller area. So the first, again, one of the first attempts in that regard was done by the Ruta all-sky survey. So this is how the X-ray universe looked in the 1990s. Now we go from the late 60s to the 90s. So This is again the all-sky map, now in artificial red, green, blue, where you see a galactic plane. The lowest energy photons are in red, and then the highest, most obscure sources you see in the galactic plane are in blue. And again, the X-ray binaries are outshining. There are some extended structures formed by supernovae interacting with the ambient medium. So this was built using the concept of the positional sensitive proportional counter. So this was again proportional counter but you had some sensitivity to anode along the anode wire where the signal fell just by the simple concept of charge division. So this itself actually improved very much, as you can see, our view, and of course, a much higher signal to noise. So in the 1990s, the ROSAT All-Sky Survey catalog produced around 18,000 bright sources. So sources which you can confidently identify with confidence above 3 sigma or so. So going from here, I would like to highlight the first X-ray all-sky survey, which was launched in 2019, which a much higher sensitivity, broadband capacity, which is comparable, let's say, to the current generation focused X-ray detectors, for example, XMM Newton. So this, the Eurocity All-Sky survey works in the energy range of 0.2 to 10 kiloelectron volts. And the way it works is that now instead of this proportional counters, we have telescopes, which can actually, these are X-ray telescopes, of course, different from optical telescopes. We can discuss if somebody has questions why they are different and how they are different. But the main concept is that you have this huge array of mirror shells, and which focuses the X-rays at a very shallow angle. And at the focal plane, you have an X-ray detector, usually a just a CCD camera, in this case a PN-CCD, which gives you enough spatial resolution to actually localize your sources to like a few tenths of arc seconds resolution in this case. And it also has sufficiently good energy resolution to be able to extract spectrum from the sources which are confined in these pixels and know more about this X-ray map. So in this way, I just wanted to show a few technical slides just for interest to go through it very quickly. So this is something called the effective area that we call in X-rays to compare different missions. So this is just the area averaged, let's say, efficiency that your X-ray telescope is sensitive to. So in the red, you see this Eurocita, and you see other contemporaneous missions in other colors, where you really see that at least in this energy band from 0.2 to 10 electron volt, it really stands out. This in the right, you see is the demonstration of the energy spectrum that I was talking about. So in black, we again have Eurocita, and in red, we have the XMM Newton, where we again see the much higher spectral capability of this mission. So with this, we arrived at this map. This is currently the most sensitive X-ray view that we have of the universe till date. So this is just from the first all-sky survey. So just to tell you in brief, this mission is in the Earth-Sun L2 Lagrangian point, and the way it rotates is that it scans the sky entirely every 6 months. So every 6 months, one can build snapshots like this of the sky. And in this manner, 4 complete snapshots of the sky was built to arrive at this image. And here I just marked the most prominent or famous objects in the X-ray sky that usually we are interested to study. You see here again the galactic plane, but now you can resolve it much better. You can see more fainter objects, which are usually actually part of this galactic ridge emission, which is a very hot topic in astronomy in general. Is what is the composition of this galactic ridge emission? And then you have the very bright X-ray binary standing out. These are structures carved out by massive stars with very powerful winds interacting with interstellar medium, so-called superbubbles. These are clusters of galaxies. Here are our neighboring galaxies, LMC and SMC, and so on and so forth. So with this all-sky map, we had 4 complete surveys from 2019 to 2022. I just wanted to highlight that the data from the first all-sky survey is already out. It was released last year. So I encourage anybody who's interested to look at the X-ray sky, or if you want to know if your favorite object emits an X-ray, please go and have a look at it. So the data release has a complete package with images, light curve spectrum, and also software and calibration database going along with it. So these are a few technical numbers. So people here who are experts in X-rays would immediately see how the sensitivity here is way, way superior than other missions, especially given that this covers the whole sky. So we can now probe sources in the whole sky to sensitivities going as low as few times 10⁻⁻14 on an average. But the way Erosita scans the sky is that you have non-uniform exposures, and near the ecliptic poles, the scans overlap, where you can go at least 2 orders of magnitude or more than 1 orders of magnitude deeper than that. And this has arrived to the point where we have, from the first all-sky survey, collected more than 1 million X-ray point-like sources. And this has doubled the number of known X-ray sources in the entire time of X-ray astronomy. So this is what we call is the soft photon pie. So you can see here a pie chart of the distributions of where the photons come from. So this is, or how the mission spent its time. So this is filter. So this is time spent on getting the particle background from the filter wheel score. So you can neglect this, but these are all real sources from the sky. So this is the cosmic X-ray background, which is a huge portion, of course, of the photons that come in X-rays, and also the diffuse foreground, which, if you look at the color code, has a lot of very interesting signs associated with it. For example, the circumgalactic medium, the local hot bubble, the solar wind charge exchange, and so on. And then the rest of it is the point sources and extended sources. I just wanted to, how am I doing on time? Yeah, thanks. So I just wanted to quickly highlight 3 very interesting signs that came out of the capability of this all-sky survey. So the first one is what is the discovery of a nova ignition flash. This is the first of its kind. So if you look at this view graph here, time versus this is the across the electromagnetic spectrum, starting from radio to infrared to X-rays. So when there is a nova, we know that it usually shows up in the optical, and as the photosphere recedes, the X-rays become evident due to the burning of the nuclear burning from the white dwarf surface. But it was theoretically predicted for many years that just before this nova goes off, there is also expected to be a very, very bright, energetic, and short X-ray flash, where the entire surface of the white dwarf reaches the bolometric luminosity before this shell is expelled. And due to this all-sky capability, and we actually discovered such an event. So you see, plus minus 4 hours, there was nothing here. And at T0, which is very coincident with a nova, we had this very bright X-ray flash. So this really revolutionized the understanding of the novae, how we understand the phenomenon of electromagnetic radiation in novae. Then we had a helium burning white dwarf. This was also a very important marker to understand the progenitors of supernovae 1A. So we have heard some beautiful cosmology talks today morning. So one of the very important probes of these cosmology is, or the expansion of the universe is through supernovae 1A. So we need to understand the population of how they are produced. So two very competing scenarios are the single and the double degenerate scenario, which means whether it's produced by coalescing of two white dwarfs or one single white dwarf exploded. So this helium burning white dwarf actually is a smoke and gun evidence that a single degenator scenario also produces supernovae 1A. I do not have time to go through this, but again, I would say that the fact that we could focus on the all-sky survey, and of course, we have a lot of multi-wavelength data and we know what to look for. This really leads to this kind of revolutionary discoveries. Then, of course, when one talks about an all-sky X-ray mission, no one can not talk about the cluster cosmology, because this is the main actually focus why this instrument was built in the first case. So I am not an expert of this, but this is for the experts in the room just to understand and absorb this information. So for the cluster cosmology, one also needs to build a mass function from a sample of galaxy clusters throughout the sky. And this was very efficiently done with eROSITA, with many thousands of extended sources with high purity class, which means the fraction of contamination is very little, and which are optically spectroscopically confirmed with the legacy survey data. So this is the common footprint. And using this high purity sample, one can also put constraints on the lambda CDM model with very high confidence, very comparable to the contemporary missions. So here's the summary of this. So in the last 50 years, astronomy has achieved like many revolutions, where we have actually arrived from few hundreds of sources to millions of X-ray objects. And I wanted to highlight this mission where I have worked with very closely, which has actually been the torch bearer to revolutionize this field, if I may say. And in the future, in the 2030s, there are also next flagship missions planned this direction. If you want to talk to me about it, I would be very happy to chat, which would further push its limits to what we have achieved. I can take just a couple of minutes to talk about related topics. So this is the team of eROSITA. So you see here, this is the software team when we went to Christmas market in 2019 or 20, I don't remember. And I just want to see that the gender ratio is very balanced here. You see 3 females here, and she actually now is our lead in the software. So this is great. So another thing I wanted to mention that I have been very fortunate to work in this team where many of the leads of both the science working groups and the software are women, and some of whom you can see here. So this has really enriched my experience and helped me to grow and really through role models. And in this case, I just wanted to briefly talk about something, because this is an equity conference. I really wanted to again highlight a talk or a series of presentation given by a friend of mine, Paula Popeso in ISO in Garching. So she has been given the series of talk about equity in perspective of a new mother, which is recently very relevant to me. So I really looked at her slides. I really encourage you to look at them, because she talks about the motherhood penalty in science, which is, I think, also a topic that might be relevant for many of us, and to think how to make situations better for the leaky pipeline. I think this is a general topic in gender equity, but the leaky pipeline happens due to many reasons for women. And of course, the responsibility of motherhood is also one of the primary reasons for which this matters. So it's not only about recruitment of women, especially at the higher stages, but it's also very important to think about how to retain them and how to ensure there's a fair environment to make progress, and especially go to leadership roles where we can have more role models. So this matters because new mothers often suffer from the imposter syndrome on having to stay with the guilt of trying to do many roles at the same time and feeling you're never good enough to do it. So these are just some primary data I could see. I'm sure many in this room are more educated with me with respect to me in this regard, but I just wanted to highlight this. And I wanted to highlight this very nice book. If you want to read it, just go ahead. This was edited and this has contributions from over 150 women astronomers from various stages in astronomy, starting from postgraduate level, which says what's been the biggest challenge you've experienced when combining motherhood and academic life. And I would like to stop here. Thank you very much.
For a very nice talk. Thank you very much. So I would like to open the floor for questions. Yeah.
Thanks for a great talk, Chandreyee. So in that E-Rosetta all-sky map, so of course, at the galactic plane, it's...
Let me try to go back.
Yeah. So galactic plane is more or less, I guess, masked because you would have...
I mean, it's highly obscured.
Yeah.
I mean,
so I'm just curious because first time I'm seeing at these wavelengths or this band, you still see that super bubble and there are things that still come through, right?
You mean the E-Rosetta bubble?
Yes.
Yes.
Can you just say a bit more about that?
Yes, sure. I mean, so yeah, I mean, this is... thank you, Mayuri. I didn't talk about it actually, because this is one of the most famous revelations that E-Rosetta made. That so you see this outflow centered along the galactic plane. This is the E-Rosetta bubble, and most importantly, thanks to E-Rosetta, we found also the southern counterpart, due to which we can really call it a bubble. So it is, of course, known from the Fermi times. It was known as the Fermi bubble, and this is the first time one found an extra counterpart of it. And the origin to this is highly debatable, and it's a very hot field in astronomy. So there are two contemporary theories, whether it is from the past activity from the Sagittarius A, or whether it's to the many episodes of star formation and supernovae which just heated the medium.
Oh, more questions? I had one question. So you showed about this image where the maps were produced like with 4 pointings. So the whole E-Rosetta image that was produced over 6 months. So I was wondering what actually is the exposure time, like how long you have to keep that integrated to produce that image?
I mean, if you talk about exposure times, so at this position in the sky, typically for one survey, yeah, you have like 100 to 200 seconds. It's not much. But if you go, here is where the ecliptic pole lights, here you can have like 5 kiloseconds, let's say, and you can multiply it by 4, these numbers roughly, to get the average exposure in the sky.
How often do you produce the image?
Not anymore. I mean, if you're aware of the political scenario.
Yeah. How often it was produced?
So every 6 months. So this whole thing took 6 months to complete, and it had a 4-hour rotation period. So every 4 hours, it basically had one complete revolution, and this way to like cover the whole sky, it took 6 months.
Right. Okay. Any more questions for Chandreyee? If not, then let us thank again for a very nice talk.